Today we're starting a new project. We're going to build a small tool that is going to render images in a very specific way using quads, which are part of a Quadtree data structure. Let me show you the end result that we're going to try to achieve. Here is our program running. It has an image loaded and currently it is showing you a single quad. And as I start pressing the buttons on my keyboard, it is going to subdivide those quads into smaller and smaller parts, and eventually we end up with a nice looking image of an owl. We're going to build this project using C, and specifically C23 standard, to make use some of its features. We're going to be using SDL to create a window and render images into that window, and we're going to be using some of STB header-only libraries. In today's episode, it's going to be STB image to simply load the data, load the image without really thinking about like the format and compression and so on. This project is going to be built in 3 steps. Today's episode is all about setting things up. We're going to be creating the SDL window, its renderer, texture. We're going to be learning how to load the image and how to show it. In second part, we're going to introduce the quads. We will start calculating the average color for each quad. We will see how we can split the quads, and we will display them using the simple queue. This will result in a somewhat good looking image, but not as good as I have shown you in the beginning. What we need to prioritize how or which quads we split next. And for that, we will need to introduce a priority queue, which we will also build from scratch. And that is the topic for part 3, where we will introduce heap-based priority queue and end up with the final result that I showed you before. I guess this is it about the project and what we're going to build. So we can jump straight into it. And as usual, let's create a repository. Let's call it Quadtree Art. Initialize some empty readme. Use C. Git ignore file. Create our repository. Once it's created, we can then clone it. We can jump into the Quadtree Art directory. Now we can create a SRC folder, assets. I have prepared a few assets like owl and I think like tomatoes. Let's copy them to our assets folder, and I have also prepared a CMake configuration file so that we don't spend too much time configuring CMake build tool. Let's copy over it here. I can show you exactly how it is configured. Pretty much there is some minimum version required. We're setting our project name to QTA, which stands for Quadtree Art. We're using C, standard 23. Standards is required, some compiler options. We're going to produce a JSON file named compile commands.json, which is going to be used by LSP server. We are requiring the SDL3 to be installed in our system, which it already is mine. We're going to compile all the C files in SRC folder, and when we link the final result, we're saying that hey, SDL3 is required for that. Let's quickly create a simple main, introduce some main function, int main void return 0, maybe press something to std out saying hi with new line. And let's try to create make file and then build, and then when we run it we should see hi. Now as usual, I need to create an alias so that I don't need to type things out every single time I need to build my project again and again. So I'm introducing an alias CM, which stands for CMake be built and CMake build. When I run it, it will compile everything again. For example, if I drop the build folder, run my CM, it does everything, and we once again have everything working. All right. So let's start with setting things up for SDL. I'm using SDL3 in this project, and what we need is we need to create a window. We need to create a renderer that is going to render things into that window, and we need to create a texture which is going to represent the thing, the frame, or the image, so to speak, that we're going to render into our window. So let's first define a structure named SDL context without a space. And we're going to say that we will have SDL window, renderer, and texture. And we need to first init, context init, and once we're done, we need to deinitialize everything, so we will have something like dinit. We will have initial context created. At the start, we will pass the pointer to our methods, and let's see how they will look like. First of all, initialization might fail, so we might as well introduce the result type as bool. Context init, given our SDL context as pointer, we can instantly say that, hey, if this init method fails, we can run context init and return -1. So if one of the steps inside this method fails, we will run the whole dinit and exit early. So what is context init? First of all, we need to initialize SDL, the whole system, and it is done usually via SDL init. It awaits some flags as input, and what we need is init video. So we're going to be working with windows and renderers, and we will need, I believe, events. So we're going to be listening to some window quit events and maybe key presses. And we can say that if this thing failed, then we can print out something like SDL init failed with some error, which SDL provides via getError function. And we can return false. Once SDL is initialized, we can then start creating our window. So context window is going to be SDL create window. Its title is going to be Quadtree Art. Its width is going to be some window width, so window height, and flags. I don't think that we need any for now. Where do we get width and height? Let's use them as parameters. And window width, window height. So when we need, let's do something like this. Pass some default for now. And then we can check if the window hasn't been created. Then we can once again print out some error, return false. And same thing probably applies to our renderer. There is a create renderer function which takes window pointer name. We won't need any specific name, so just null is fine. Then we can do our error checking. Renderer, create renderer failed. That was quick. And finally we need to create a texture. that is going to be representing our image. So context texture is going to be SDL, create texture. Render is something we already created. Pixel format. I'm going to be using some alpha RGB 888, so 32-bit, 8 bytes for each channel, alpha channel, red, green and blue color channels. Texture axis static is for something that doesn't change much. We're going to be using streaming because we're going to be changing things in our texture quite a bit. And width and height will be the same as our window. And then same error checking applies for our texture. Create texture failed. And if everything is fine, we can return true. When our init method succeeds, we are fine to go into some main loop here, which we're going to need to introduce. But before we do that, let's think how we can deinitialize everything once we're done. Context deinit, given our SDL context, we can check for things like we need to destroy things in reverse order. So if we created window first, then renderer, finally texture, we will drop them texture first, then renderer, and finally the window. So SDL destroy texture, given context texture. Then we can destroy renderer, and we can destroy window. And the only thing here is that because we can fail at any step in our init method, some or all of these context values can be null, and we can safeguard by checking whether the value is actually set or not before invoking the destroy method. And finally, when we have destroyed everything, we can say, hey, SDL quit. And I think it's fine to call it even if our SDL init failed in the beginning. It should be quite fine. So let's build our project. Let's try to run it. There are no errors, but we also don't see any windows. And what happens here is that once everything is created, we jump into the destroy part right away. To see the window, we need an actual main loop. So let's write it out. Let's introduce some flag bool quit, which is false. Main introduce like while not quit, right? We do something, and this will show the window itself, but the window will be unresponsive because we're not handling any events. I will not run it in this particular configuration, as it will take time to close the window. So let's do it correctly right away. There is an SDL event which we can use, and we need to poll the events. Poll event given our event, and while we're polling, right, now everything should work. The window becomes responsive, and the only thing that I want to do is to make sure that we can close the window. So if event type equals to SDL event quit, right, we can set our quit to true, and this should quit the window. Let's try running that. We can see our window, it's responsive, and clicking the close button closes it successfully. So this is pretty much everything that we need in terms of SDL. Let's think about our main loop a bit more. So once we have polled all the events, we really need to do something. So eventually we will need to draw an image here, probably given our context. So let's introduce a draw image function, SDL context. Right, it can even be a const, saying that we're not going to be changing it. So to draw something, really we will need to manipulate our image. As you saw in the beginning when I showcased the final result, we're going to be loading some image, we're going to do some manipulation with it, and then try to render our manipulated version onto the screen. We will not be able to do that, or maybe it's possible, but it's definitely more difficult than what I want to do. I want to introduce a thing called Framebuffer. Let's name it Framebuffer. So this Framebuffer is going to be a simple array. So it's going to be uint of some data. It will have some width, it will have some height. And this Framebuffer will be used to load the image. We will use we will load the image, and once we process the image, we will write the processed data into Framebuffer and then copy it over into our texture. Let me show you how we can do that. So suppose that we have done some manipulation and Framebuffer is already filled with something that we want to render. We will need to say that, hey, SDL update texture, our texture from context. We will not use any specific boundary. We are saying update the whole texture. That's why we're passing null here. Pixels is going to be context Framebuffer data, and pitch is about the width or number of bytes in a single row. So that's going to be size of uint times context Framebuffer width. So our Framebuffer has a width of, let's say, for example, same as texture, window width, and it is represented by 4 bytes each pixel. So it's alpha, red, green, and blue. That's why we're saying that a single row takes this amount of bytes. And once we have updated our texture, we can say, hey, render this texture using our renderer, using this texture. And once again, we're saying, we don't need any boundaries, just use the whole space available. And then I think it's render present. Was it renderer, I think? Yeah, it takes the renderer. Let's try running that, and I think we will see some issue right away. Yeah, it fails because our Framebuffer is not initialized. So we have put it into our context and we have initialized everything but the Framebuffer. So we need to do that as well. Let me initialize it first before we initialize SDL. Let's say context Framebuffer is simply malloc size of Framebuffer. If not context Framebuffer, right, there is some error. So fail to malloc Framebuffer, except there is like no SDL error anymore. And then we need to also malloc the data. So we need to say that, hey, I need to malloc times window width and height. So it's taking like the same amount of data as our texture, as our window is going to be rendering. Again, we can do the error checking, saying that if we fail to do that, Framebuffer data, Let's see whether it improved things. Now we can see something crazy going on, and this happens because we are successfully allocating data, but we receive some random chunk without writing into that particular chunk of data anything. So we are viewing the trash that is currently there. So let's try to clear that frame buffer. How can we do that? So let's do it this way. For size t row, probably context frame buffer height. It's actually going to be from 0 and row is less than height. Then for size t column, which is from 0, column is less than context frame buffer width. Right, we want to say that, hey, context frame buffer data at what position? It's a row times context frame buffer width plus column, and we're saying that this is going to be black. So if you remember, I'm initializing the pixel format as alpha first and then red, green, blue. So my alpha is FF, saying that it is opaque, and then everything is 0. That means it's black. It wants these values to be of the same type. If we run it now, we can see that nothing really changed for some reason. Oh, interesting. Why did that happen? Draw image. It's because we haven't actually set the frame buffer values. So context frame buffer width is window width, and context frame buffer height is window height. This should probably be it. Yeah, and now we see black window. So for example, we can test it out and make it red. And yeah, looks like it's working. Let's get it back to black. So right now we have something that for each frame clears our frame buffer using black color, and then copies this whole frame buffer into the SDL texture, and the renderer then presents or renders this texture onto the screen. So our next step is to load an image and probably show it using the same frame buffer. How do we do that? We need to first go and find the STB image, the one I showed you in the beginning. Use some raw, we can just copy it. We can then create STB image h. Right. Now, if I go and include it in my main, include STB image h, and it also says that you need to define this before inclusion so that everything is enabled, then my LSP breaks. And this happens because once you include the header file, it's copied into this file, then it tries to rebuild, and it's different from CMake. There is like a lengthy explanation of why it doesn't work with LSP well, and the workaround is to actually create a C file, STB image C, which we can then, where we can put the flag or this define that enables the implementation, we can drop it in my main file, and this should be fine. Now, as we talked about LSP, I totally forgot about one thing. So in my build folder, there is a compile commands JSON, which my LSP wants. It is currently not needed because we're working only in main.c, but once we introduce more files, more header files, and you want to jump to definitions, our LSP will need that JSON file to find out where everything is. To help our LSP, I need to link that file. So build compile commands JSON here. You can see that here it's linked to this build, and my LSP will be happy. Once we introduce more header files, then we will be able to jump between them without any issues. But for now, we can get back to this STB image and see how we can load things. In order to load an image, we probably want to provide an image via the argument. So let's do that. Int argc char argv. Let's say that if argc isn't 2, we can say that usage is something like this. Argv 0. So if I run it without an argument, it says, hey, please use some image. It has an input param. And if I use something like owl, it shows me a window, but doesn't do anything with the provided argument. That is exactly what we're going to do next. Let's see. Let's define some structure for our image. It's gonna have some bytes of raw data. It will have some width, it will have some height. And now we can use a function from STB image, STB I think it's load, which says file name. That's gonna be our argument. It wants not only, as a result, this function not only will provide the raw data of the image, it can also give you the width, the height, the number of channels. So these are like these 3 params. So if we say that we have an image data is going to be returned by STB load. We want to save the width in our image width, the height in our image height. Channels we don't really care about, so we can pass null, and the number of desired channels is 3. So depending on the file format, it can be composed of 2 channels, 3 channels, 4 channels. And we want to unify it, saying that, hey, the library, please always provide me 3 channels, which ends up to provide R, G, and B values, regardless of the image format that we load. Now, once this is loaded, we can check if it succeeded, once again, by checking the data. If it's not, we're sure that something went wrong. Failed to load image. argv1. Let's see how it goes. So if I say something that doesn't exist, it says failed to load image. And if it does exist, everything works fine, and we're showing the window. So at this point, our image contains all the data, and we would like to show this image in our window. So first of all, I would like to create a window which is using the same width and height as our image. So instead of hard-coding these values, I can say that, hey, please use image width and image height. I have also selected the images that fit my screen for now. And as a exercise to you, you can think how you can then render those images which have like much higher dimensions than like your screen, so that the window doesn't fit fully. You can use the aspect ratio of the image and apply it to the window width, but continue texture and frame buffer manipulation using the whole image width and height. This is not like part of our project, but this is a very nice exercise for you. For now, we're simply using images which fit the window, which fit like the screen that I'm using. Alright, so once we have initialized, let's see like whether our window has changed. Yeah, it's definitely using some different width and height than before. And now we would like to probably show this image. How can we do that? Let's simply do it here. Let's pass it to our draw image. So it's going to be pointer to our image. This is simply like clear frame buffer with black. This is something that we will need later on in the project. For now, it was just showcasing how our frame buffer works, how we can manipulate it and then provide it to the texture so that it is drawn on the screen. Right now we will fully override it with the image data. How can we do that? Let's think. Let's do it this way. That for size t row 0, row is less than image height. Size t column 0, column is less than image width. The main thing to remember here is that we must make our image height and width is the same as our frame buffer, or vice versa. Probably frame buffer must be of the same dimensions as our image. Right now, everything is of the same size. Window, texture, and frame buffer are all of the same size as in the image. But if you decide to make those aspect ratio adjustments that I talked about previously for you as an exercise, then you must remember that frame buffer has to keep its dimensions the same as the image. Alright, so once we have that, we're saying that, hey, let's write things into the frame buffer. So context frame buffer data, we're gonna write somewhere, gonna write something. Something is gonna be some sort of color. Color is 4 bytes, and it consists of, first of all, alpha. Right, we need to bit shift it to the left so that it takes the first 2 positions here. Or then we take image data, some offset, right? Offset, which represents red, bit shift by 16. Then there is an image data offset +1, which is green. And finally, image data offset +2, which is blue. So what is this offset? What is this offset? Offset is row times image width times 3. As you remember, when we load it, we're saying that, okay, image has some specific width, and we asked to load it with 3 channels. So every pixel in this width is represented by 3 pixels. And when we are on specific row, we need to skip these many bytes before we reach the column. That is also multiplied by 3, because inside the column, each pixel is represented by 3 values RGB. So this is the offset. When we read data from image. And we construct the full color, which is 4 bytes, alpha, RGB. And now we need to think like, where do we put it? And we put it into, I think it's the same as like row times, I mean, I can write context Framebuffer width plus column. I think this is it, except that this thinks it wants it to be ints because image height and width are ints. Let's see what it does. And here it is. This is our image. So we're pretty much done with the first part. And in the next part, we will introduce the notion of the quad. We will talk a bit about the quad tree, how we're going to be initializing our quads. We will be calculating the average color of the quad, some standard deviation of this quad. We will learn how to split those quads and how to draw them or render in the same draw image function. But that is it for now, for today. If you like this kind of content, please do like this video and subscribe. It helps me a lot. Thank you very much and see you again.